On to the next item is our second speaker. Kevin Sellner is here to present an overview and summary of his findings of the analysis of the Monocacy River water quality. So good evening, Kevin. Would you like to say a few introductory words before I start your PowerPoint?
Sure. Go ahead. Bring it up, Tim, and while you're doing that, I'll I was working at, I'm retired, oceanographer, limnologist now, and I worked with Drew Ferrier over at Hood College, the Center for Coastal and Watershed Studies. And we put this together some two and a half years ago. Gary Magnuson was very important to us in helping us scope out what we wanted to do, and then next steps and getting a little bit of funding for some students to analyze some data, etc. The reason for the analysis was because of the Monocacy River Scenic River Plan discussions that you've all alluded to. And so we wanted to have the data that are available actually speak for the river and let the data inform the county council and county executive. And from those data, they could then make their decisions. So anyway, with that, so I'm a scientist, and Drew Ferrier is also on the line. So if we start to get too technical, just start waving. You know, we have our own jargon, unfortunately, that sometimes is just, you know, it's common to us, but it may not be understandable to you. So please interrupt. It may be too long. So if that looks like that's going to interrupt the rest of your evenings, then just give me a heads up, maybe 20 minutes in or so, Tim, and I'll go faster or jump to the end, something like that. Okay, so can I have the next slide, Tim? So putting the key findings up now, because in case I have to jump because of time, I just want you to know what we found in this analysis of 33 years of river data that DNR has been collecting monthly since 1986, and we analyzed through 2018. There are two nutrients we looked at, phosphorus and nitrogen, both of them required by all plants in the water, on the ground, in crops, trees, etc. Every single plant out there requires phosphorus and nitrogen. So the key findings are that phosphorus concentrations are highest at the Pennsylvania-Maryland border at the northernmost station, and downriver concentrations decline due to contributions from Big Pipe Creek, which primarily drains from Carroll County. A wastewater treatment plant at the city was installed in roughly 2002-ish time frame. And that made a tremendous impact on reducing phosphorus concentrations further down the river. Next bullet, Tim. The river nitrogen, on the other hand, in contrast to the phosphorus, it's actually derived from Big Pipe Creek, so primarily from Carroll County. It is essentially, there are smaller increases, and we'll see those data in a little bit as it passes through the county, so that the county is adding nutrient to the loads that are coming in from our Pennsylvania neighbor to the north. Next one, Tim. They've generally declined, all nutrients have generally declined in the time period. Frederick County and city still remain sources of nitrogen, though, as the river passes through city boundaries. I'm sorry, the county and the city boundaries. Next one. The nutrient increases in the county are primarily from agricultural activities, and that's, you know, not unexpected since agriculture dominates the industry of the county. But the most rapidly increasing source of nutrients in the Monocacy watershed is development, and that's actually true bay-wide in the bay-wide watershed. Next bullet, please. And we did an analysis that allowed us to identify seasonal patterns. In other words, you know, we know when maximum precipitation occurs historically in each season, and then there are deviations from those seasonal patterns that have to do with major storms. And you'll see some of the results from that. And those major storms have some implications for what the city and county might do in the future to address these intermittent loads that are coming in. And that's being addressed in the climate emergency resolutions that the city and county have recently passed. Next slide. Okay, so the basic background is that all rivers transport land-derived nitrogen, phosphorus, sediment, and other materials. And we'll get to those other materials in the end. The nitrogen is found as these pools of total nitrogen. That's every single nitrogen-containing compound. Dissolved inorganic nitrogen, which is the pool of nitrate, nitrite, and ammonium. And those are the two NO2-3 and the NH4. Those are nitrate, nitrite, and ammonium. So those are basically the 4 to 5 pools that make up nitrogen in the river. Phosphorus is found in only 2 pools, total phosphorus, meaning all phosphorus that's in particles and dissolved, and then orthophosphate, which is inorganic. That is, it is not in any organic material like plants or animals or anything like that. There is also organic phosphorus and organic nitrogen, but they're lumped into the TN and TP categories. So as I said earlier, nitrogen and phosphorus are critical macronutrients for all planktonic, that's free-floating algae, and benthic algae. Those are algae that inhabit the bottom. And cyanobacteria. Cyanobacteria you might know as blue-green algae. Most people think of it as that scum that forms on the top of farm ponds and Color Lake, etc. And then submersed grasses. So if you go out in the Potomac, and maybe Andy knows this from his fishing, you see lots of submerged grasses kind of flowing with the current. Well, nitrogen and phosphorus supports the growth of all of those. The eventual decomposition of those pools of phytoplankton, the planktonic algae, the benthic algae, the cyanobacteria, and the grasses leads to that bay hypoxia or anoxia, which has driven the bay-wide implementation of the total maximum daily load that's allowed across the watershed. And that's basically telling each community, each county, municipality, how much nitrogen, phosphorus, sediment that they are allowed to dump or release into the receiving waters that basically then go down and support the growth of those organisms I just mentioned. And when they decompose, it creates the bay hypoxia that is driving these regulatory management requirements that we now face since 2010. In the beginning, there were multiple statements that were made that since the Bay is getting better back in a couple of years ago, and that's basically the Bay Foundation and the Bay Program and other organizations were concluding that. Then the conclusion was that we must be doing better too. The county must be doing better. And that if there was any problem, it was obviously coming from our neighbor to the north. It wasn't us because we were very stringent about what we were doing with our loads. So that's why we undertook the study. Next slide, please. So here's a map of the county and the watershed. You can see the upper part is basically in southern Pennsylvania. And then you can see the 5 stations that Maryland DNR has been collecting samples at and analyzing data since 1986 into the present. You're going to see references to, rather than these station designations and numbers and codes, I tried to make it so that you would see it as Pennsylvania border, Carroll County introduction, north of the city, below the city, and then just north of the Potomac. So those are the 5 stations. And we analyzed the data from those 5 stations for that time period. Next slide, please. So I don't want you to get anything from this other than look at the extremely high variability. That's all that you should be looking at here. The river is a function of precipitation events, drought events, snow melts, etc. The concentrations in the boxes at the top give you an indication of the average concentrations of the nutrients over that 33-year period. Don't try to memorize this because I'm going to get into a graph, the easy to understand graph in a couple of slides. But basically you can see the Pennsylvania border basically has a higher level than what's coming in at Big Pipe Creek. And then south of the city, you can see that the numbers jump up again. Next slide, please. Okay, so the way we analyze these data is we plotted all of the data out, and then we set up two different models, mathematical models, to tease out patterns that would be in the data. And the teasing, you can see the very high frequency up and down patterns on the one that says season. And that's basically the concentrations of phosphorus that would be occurring in the 4 different seasons. We've removed all of that variability so you can see the bottom line results over on the right side. And the take-home message for this is that the highest concentrations of dissolved phosphorus are found in the summertime. That's the red line. They are slightly lower in the fall. You can see the yellow, barely see the yellow line. And the lowest concentrations are in the spring. So that's the seasonal pattern for dissolved phosphorus in the river over the 33-year period. Can I have the next slide, Tim, or next button? Now you look at this one, and it's a repeat of the slide on the upper left, but we've added in flow. So variabilities in flow will alter that seasonal pattern. And the magenta, or that pink color, you can see the very high peaks, low peaks associated with this graph. And those represent the impacts of extremely high flows, that is big precipitation events and the river increases in volume, or droughts, and that's the lower, the pink that's going below the average concentrations. And so that high variability, much higher than what you see in that pattern in the upper left, that high pink variability indicates that major precipitation events or their absence, such as in droughts, does have a dramatic effect on the river nutrient concentrations, in this case phosphorus. And the implications of that are that with our new climate, the climate that is here and projected through 2100, basically will have much more intense precipitation events. They'll be more frequent than they are now, and then they will be separated by periods of drought. So that high variability in the pink that you see below in that lower panel means that we have to consider various practices that would alleviate, that would reduce that variability. We don't want huge pulses of nutrient going into the river at any time. We're trying to keep those reductions or the loads quite low. Next slide, please. Okay, what happened? Well, here's a result of the station just below the city of Frederick. And you'll note in the oval, there seems to be a rapid decline in the concentration of the dissolved inorganic phosphorus. So about 2002, and for a while, we were asking the various county staff what could be the possible reason for this. Because if you do that pattern that I was saying, if you get an average concentration over this, you actually miss what might have happened to explain this large decline. So we went in and we actually found through some conversations with the city that in fact they had implemented biological nitrogen removal and phosphorus precipitation in about November 2002. And so the result is this rapid decline, large decline in this dissolved inorganic phosphorus. So it has major implications for what the lower part of the river has in terms of this macronutrient that it's exporting into the Potomac River and then further down bay. Next slide, please. Okay, the implications of that decline are pretty evident here. You'll see in this contrast. So looking at the whole data set, the phosphorus that's coming in at the Pennsylvania border is essentially just slightly greater than 0.1 milligrams per liter on average for this 33-year period. And then the water that comes in from Carroll County in Big Pipe Creek is much lower. So when those two creek and river mix, then in fact it's going to lower the concentration because it's not an additive process. You're diluting the higher concentration that's coming in at the Pennsylvania border, and that results in that first blue arrow that's moving from left to right. And so at north of the city, that dilution has occurred from Big Pipe Creek, and you can see that the concentrations by that blue arrow, meaning that they are significantly lower just north of the city. Now, once it passes through the city for the 33-year period, you can see that it jumps up. And then why would that be? Well, if at the time prior to 2002, as I was saying from that jump, there was no removal the removal of phosphorus was not very high. The BNR and the other phosphorus reduction strategy hadn't been implemented. So in fact, the city was adding phosphorus to the river as it passed through. So that arrow that's going up, the second arrow that's going up, indicates that city contribution. Further downriver, it's being diluted by land use practices, etc. So you can see there's a slight significant decline further downriver. But what is entering the Potomac is higher than what came in at the Pennsylvania border. Okay, next click. Okay, now if we analyze, because of that jump or that decline in 2002, we knew we had to analyze the data for that 2002 period on, because you couldn't very well say to the rest of the, to everybody who's interested in the river, well, geez, it looks like there's a major problem that would be evident from the panel on the left. Well, the implementation and construction of that wastewater treatment facility in November 2002 dramatically changed that downriver pattern. You notice that you'll still see the dilution of the phosphorus coming into Pennsylvania border by Big Pipe Creek's water and lower phosphorus concentrations. So just above the city, you can see that it's declined from what's coming at the border, but the construction of that plant with that new capability, rather than having the increase that you see south of the city in the left panel, we actually see that the concentration is much, much lower. And in fact, the equal sign means that there was no statistical difference between any of the average nutrient concentrations for that time period for those three bars. So this wastewater treatment plant upgrades in November of 2002 have dramatic implications for what is being added downstream of the city, and importantly, what's going into the Potomac. Because look at the magnitude of the bar on the extreme right. It's about half or so of what's on the bar on the left-hand panel. So that phosphorus upgrade in 2002 had a dramatic and positive effect on that phosphorus concentration. What that would imply is that for the Potomac and then the receiving waters of the bay, at least what we were doing in Frederick County after November of 2002 for phosphorus was an improvement over what we had done historically. Okay, next slide. All right, now we're going to jump over to nitrogen. Nitrogen is a reverse of that pattern in a way. Notice that the Pennsylvania border nutrient concentration is on the order of 1.3 milligrams per liter, on average for the 33-year period. If you look at the panel next to it, Big Pipe Creek average is 3.2 milligrams per liter. So in contrast to the situation with phosphorus, where Big Pipe Creek diluted what was coming in from the Pennsylvania border, Big Pipe Creek nitrogen is actually enriching what's coming in from the Pennsylvania border. Next slide, please. So here's a repetition of those very busy slides before. Again, these are just to show the seasonal patterns. Again, note the high up and down variability of those of the black line. That's the seasonal pattern of nitrogen concentrations in the river. And then we're removing all of the not the noise, but the variability. You can see that in fact the seasonal pattern is different from what we saw with the phosphorus. Phosphorus was higher in summer and fall. Here, nitrogen is higher in the winter and spring. And in a way, that's what you kind of guess, because nitrogen is dissolved primarily in the dissolved state. And when snow melts, it basically carries that soluble nitrogen down into the river. So you get a big pulse of dissolved nitrogen accompanying the winter thaw and spring runoff from precipitation events. So again, different pattern than what we saw with phosphorus. Next slide, next bump, sorry. Now here you see, again, just like with the phosphorus, the very high variability with the pink, the magenta color, that's associated with extreme weather events. That high variability in nitrogen implies again that in fact we would have to pay close attention to either extreme precipitation events to bring in more nitrogen, or the droughts to in effect reduce the amount of nitrogen that's coming in from the land. The implications for climate are, because again, as I said earlier, because the new climate is going to have these more frequent extreme storms and then separated by longer periods of drought, we must take that into account as we try to manage the loads of nitrogen and phosphorus to the river. Okay, am I too technical here? Is it okay? Is everybody okay with this? Okay, good. I saw one thumbs up. That's good. Next slide, Tim. Okay, so what's the pattern, 33-year pattern for nitrogen? You can see that the Pennsylvania border is fairly low for nitrogen, and that basically is enriched by the addition of nitrogen that comes in from Carroll County's Big Pipe Creek. That results in an increase, a significant increase in the river's nitrogen north of the city. That's that first blue arrow that's moving up from left to right. And then as it passes through the city, there's again an increase, a slight increase that's due to the city's contribution, urbanization, suburbanization, etc. That's adding in nitrogen. Okay, that's for that entire, and then that does not change as it moves downriver to just north of the Potomac. And that's, again, the 33-year period. Let's look at the pattern after the improvements. Okay, so here's the same story again. You can see that, in fact, north of the city, the concentration is increasing for that 2005 to 2018 period. It again increases from north of the city to south of the city, but notice that the height of the bars is lower, so that the amount of nitrogen coming in from urbanization, suburbanization is significantly higher, but only slightly. And then from south of the city to north of the Potomac, where the Monocacy enters the Potomac, there's also just a slight increase in nitrogen. Again, meaning that whatever land practices we have in the county, we are adding nitrogen at levels that are altering the concentrations in the river by a significant amount. Even though it looks like a small number, the amount of nitrogen as it passes through the county is actually increasing due to our land use activities. Okay, next slide. We also measured total suspended solids and chlorophyll. Total suspended solids are interesting because that's what governs the amount of light that comes in and into the water and then passes through the water column. And total suspended solids often includes sediment particles to which phosphorus is bound. Most phosphorus comes into receiving waters bound to sediment particles. Well, there was very little significant change in TSS over the time period, whether 33 years or the shorter 2005 to 2018 period. For chlorophyll, the reason we looked at chlorophyll was if those macronutrients are coming in to the river, was there a river response in terms of the algae and the cyanobacteria that were in the river? And again, there were some slight differences, but nothing that would indicate a major eutrophication problem. So the nutrients were largely passing through the county without actually fueling a lot of production of algae and cyanobacteria. So we weren't loading the Potomac or the Bay with biomass that would break down to cause hypoxia and anoxia. We were loading with nutrients, but not with actual particles of algae. Okay, next slide. Okay, so one of the thoughts was, okay, land use, as I said in the opening slide, you know, because agriculture is our dominant industry, you know, it was likely a major source of nutrients. And again, if development was our major industry, it would be the same for development. But it was brought up like, okay, what about all the wastewater treatment plants? Are they the cause for what we're seeing in the river? Well, my colleagues at the Chesapeake Bay program collected all the data from the major wastewater treatment plants in the county. And basically the take-home message is that the concentrations for the major wastewater treatment plants are quite low and likely do not explain the elevated concentrations that we saw of nitrogen phosphorus in the river. You can note at the extreme right side of these diagrams that in fact the red line is tending down to very low levels. At least in the two panels in the upper row. Can you go to the next slide, Tim? So what we did is from that, we said, okay, wait a minute, let's put the whole picture together. We've got agriculture as a major industry. We've got wastewater treatment plants for the increasing populations within the county. Let's look at the model output of all of those loads and see if it agrees with kind of what we were contemplating for explanations of the nutrients in the river. Well, here what you see is basically the upper river, which is above north of the city, mid-river, which is just above the river, above the city, and then lower is below the city. The size of the pie represents the magnitude of the amount of load of that nutrient coming into the water. So the bigger the circle, the more nutrient coming in. And you can see that in all cases for nitrogen, it's dominated by blue, and that's agriculture. However, if you start summing up regulated development, non-regulated development, wastewater, and septic, they turn out to be an increasingly important piece of that pie because it suggests that, in fact, as we urbanize and suburbanize and we build homes for the new population, that, in fact, that load is going to go up through time. If you move to the phosphorus situation, again, ag is the major source in the upper portion of the watershed. And then the other components, other parts of land use become more dominant and more important in the lower portion of the Monocacy watershed. So all of this gives us kind of an insight of, okay, what do we do in the future to try to ameliorate and reduce these overall loads? Can I have the next slide, Tim? Oh, okay. So when I mentioned in the beginning about other compounds, there are other things in the river that we did not analyze, we don't have data for. Extensive time series data like the 33 years I was mentioning for nitrogen, phosphorus, and sediments. But there are things that are coming in from ag and from urban, suburban areas, like herbicides and pesticides. Some of these compounds do cause intersex in fishes. Intersex meaning that a fish can be both male and female. And that does have dramatic impacts on fecundity. The number of those fingerlings that were talked about earlier when we were discussing Lefty. And those compounds can also lead to compromising the fish's ability to deal with stress, whether it be a pathogen like a bacterium, like a fungi that would infect an open wound. So those things are a big concern for, and particularly I would think for fishers, because those things can reduce fecundity of our, particularly our smallmouth bass populations. If you look at the macroinvertebrates, DNR and the county actually go out to these creeks, all the creeks that feed into the Monocacy tributaries, and you scoop up the sediment and you analyze the little animals in that sediment. Those are called macroinvertebrates. In most of these small tributaries in the Monocacy watershed, they are poor to fair, meaning that in fact, the Monocacy problems that we're seeing in terms of elevated nutrients may also be characterized by similar conditions in these small tributaries. So it's not just the Monocacy that's having these problems, it's the small little creeks that are feeding into the larger creeks and rivers that then feed the Monocacy. We also know that Fort Detrick has substantial, over 3-4 decades of burying parts of its contaminated materials on site. And so those things are leaking or volatilizing, and they can go into the receiving waters. And the current focus areas are trichloroethylenes. And these compounds essentially dump into Carroll Creek, which come into the Monocacy. So those are things we have to be concerned about. Drinking water plants produce halogenated. Halogenated means bromine, chlorine, elements are added to various organic matter that come out of drinking water plants. And if those levels get too high in the river, then in fact they can pose human health problems. And they have not caused those problems, so no worries right now, but they are being monitored by the county and city routinely. And then finally, that warmer climate that we're now experiencing, we select for this group called cyanobacteria. And these cyanobacteria can be in the water column, and as I said before, they can be like the scum that you would see floating on the surface of a pond, or they can be on the bottom. And some of them produce toxic compounds that are toxic to wildlife and to our fellow citizens, residents, fishers. And so there is some concern, and we've talked with the Council of Governments and city and county about how they're treating their waters. So far, with the concentrations of these compounds that we're seeing, we're fine. But in the future, as it gets warmer, only this group of organisms will be prevalent in our waterways, which means we'll have to be even more diligent about these toxic compounds that are being produced. So next slide. Okay, hit it again, Tim. All right, this is just a repeat of what I said in the beginning, and I'll just go quickly. So the phosphorus concentrations are diluted by what comes in from Big Pipe Creek. The implementation of that sewage treatment upgrade in Frederick City in 2002 has led to substantial reductions in phosphorus. Next one. River nitrogen is actually increased by what comes in from Big Pipe Creek and Carroll County. It drains Carroll County. And there are reductions that are occurring through the plant, but there are still increases all the way down to the Potomac. They're small, but they're increases. The general pattern is there's a decline through time, and that's very good. But again, it's still that we're increasing as the river passes through the county. Right now, the nutrient loads are primarily from ag. Again, the largest industry, not too surprising. No industry can be 100% perfect in terms of preventing any nutrient inputs. So, if, as I said, if development became your #1 industry, it would have the highest loads. So, and then those pink magenta line, the high variability in those lines suggest that in fact major storms and droughts do have impacts on the river in terms of drastic modifications of those concentrations. So as our new climate comes in with these extreme weather events and separated by these droughts, we have to start thinking of new implementation practices to reduce the threats from those loads. Next slide. Okay, what do we want to do? Well, up in Big Pipe Creek, that drains Carroll County, but it merges with Little Pipe Creek. And Little Pipe Creek is receiving contributions from Frederick County and also from Carroll County. So when the few data that we have for Little Pipe Creek suggest that, in fact, the nitrogen concentrations in Little Pipe Creek are actually quite high. So could it be that Big Pipe Creek from Carroll County mixing with waters from Little Pipe Creek from both Frederick and Carroll County are resulting in those elevated nitrogen concentrations that are driving up the Monocacy River concentrations north of the city? So we need to go in and look at Little Pipe Creek, and I'll get to this point in a minute. What are the nutrients that are associated with these high variability, these pink peaks? Is it nitrogen that's driven by low flows, high flows? Is it phosphorus that's driven by those? There are models out there that we can use to tease out these contributions, but the models, this mathematical way that you look at water flow and land use loads to that water flow, generally are limited to systems over 100 cubic feet per second. So they're not the smallest streams, and in fact, the smallest streams and rivulets may be major sources that we won't be able to estimate. And forget the next one, we can go to the next slide. Okay, so there is a phase 2 to what we've done. This first effort was a phase 1. And the 3 areas that you see are potential hotspots, either for nitrogen, phosphorus, or both. And so, as I mentioned above, what about Little Pipe Creek? That's that oval red area up in the northern part or northeastern part of the county. Should we be sampling there at in the little tribs where they join Little Pipe Creek, and then at Little Pipe Creek where it joins Big Pipe Creek, to find out if we can identify, are there sources and land uses that we can potentially work with the owners of those lands to say, hey, here's some incentive, here's some tax breaks, here's some ways that we could actually reduce the loads from your particular land use activity. And we can do that in summer. Summer base flow means when precipitation events are essentially in those drought periods, most of the load is coming from groundwater. It's not coming from surface water. So that's particularly important because it tells you what that background level of nitrogen, particularly nitrogen, is. Next bullet. So after we would get those data, the idea was then to identify those land uses and where there might be issues with loads that are coming in, nitrogen, phosphorus sediments, and then look for those unique opportunities, whether they be all public, whether they be public-private partnerships, whether there be some unique financing opportunities that we could do to essentially reduce the loads from those particular land uses. Next one. Finally, the land options that are out there to ease some of these problems are actually on many of the reports and documents that the county and city maintain right now. And it's where we drew upon many of those documents to come up with some of these isolated nutrient concentrations. For example, for Little Pipe Creek, for some of the very small tributaries that are coming in south of the city, etc. The current climate emergency mobilization work group, which I co-chair, is undertaking an analysis of these types of systems to find out, okay, are there practices on the land that are actually going to increase the productivity of that land practice, of that land use, that would also reduce the loads that are coming into the system. So that will be one of the goals, and that series of recommendations to the city and county are requested by the end of September or mid-September. And finally, the Interstate Commission on the Potomac River Basin has just worked out a project with Maryland Department of the Environment and National Research, NRCS, to study the Little Pipe Creek for just the types of thing I was talking about above. So we may be able to partner with them in terms of understanding where the load sources in Little Pipe Creek and what can we do to change those load patterns in the future. Next one. So with that, I'd like to end it, and I'm sorry if it was too technical. I didn't hear anybody screaming that it was over their heads or anything, so I hope it was okay. And Drew Ferrier, my collaborator, is on the line too. So at any time, whether it be now or in the future, you want input, dialogue, data, etc., we can interact with you easily. We work with Gary Magnuson pretty often, and Gary can be an easy conduit to us if you don't want to come to us directly. So,
Kevin, thank